order subtractor 4 bit. So this is an example of a combinational circuit. So ripple carry order is something that you have already seen, where you have 4 full order 0, to which you give say A0 and B0. Then you have full order 1, to which you give A1 and B1. Similarly, you have full order 2, to which you give A2 and B2. So there are 4 full orders which are performing bitwise addition. I am naming them as FA0, FA1, FA2, FA3, and to FA3 I give A3 and B3. So A is a number which is A3, A2, A1, A0. So it's a 4-bit number. A0 is the LSB, least significant bit, and A3 is the MSB. Similarly, B is the second number, which I am denoting as B0, B1, B2, B3. And our purpose is to add these two 4-bit numbers. Okay, so if we have to first start with the LSB, normal addition procedure is you add A0 with B0. Whatever is going to be the result, it may be 2-digit result or a single-digit result. So whatever is that result, LSB of that result, we call it as S0, and the other bit is going to be the carry that you have to add with the next position. So we can call it as C0. So C0, or let's call it as C1. Okay, C1 will be added with A1 and B1, and that will also generate some 2-bit result, which we will call the LSB as S1, and the MSB of that 2-bit result we will call it as C2, and that will be added here, and that will give you S2 and C3. Finally you will get S3 and C4. So this is the case. Okay, so that is just the order itself. So you have S0 here, S1 here, S2 here, S3 here, and then carry. The carry input here C0 is given to the first position, and for addition purpose you give it as 0. And the carry out, which I call it as C1, that goes into the input of FA1. And then similarly for FA1, carry output is C2, that goes to FA2 input. So full order has 3 input and 2 output, as you can see in each of this case. So this is C3, and the final carry is part of the result, so which is C4. So this is just order. Now if you want to make a subtractor in a similar way, we have to adopt 2's complement representation, in which the number that you want to subtract will be considered as a like for example, if I want to do a minus b, then what I do is I will consider it as a plus minus b, a plus minus b, and where minus b will be expressed in 2's complement form. Okay. Now, what is the way to express minus b in 2's complement form? That is basically you take the 1's complement and add 1 to it. So how we can do that here? Okay, if at all we have to perform a minus b, how can we make use of the adder circuit to perform, because you are basically adding a plus minus b. So adder circuit can do this addition of a plus minus b, provided the minus b is available in 2's complement form. Okay, so in order to make minus b possible, what we do is like each bit can be complemented, each bit of b can be complemented. So let me redraw the circuit now in such a way that I am able to do a complement. So let me take S0 here, and instead of B0 I would like to give B0 complement. So what can I do? I can just take a NOT gate and give this. So I give B0 here to the NOT gate, and the NOT gate will make it B0 bar, which is the complement of B0. So this is what is coming into full adder 0. And then after complementing each bit, I also need to add an additional 1 in order to take the 2's complement. So the procedure to take 2's complement is complement each bit of b, and then add 1 to it. Okay, so this is the procedure. So in order to make an additional addition of 1 to the complemented bit, what I will do is that the carry bit input to the FA0 full adder, I am going to give it as 1. So C0 I am going to consider it as 1. C0 now I will give it as 1. So complementing the bit of B0 is done by NOT gate, and addition of a final 1 after complementing everything, that is accomplished by setting the carry input C0 to be 1. Okay, so then everything as before, you give the carry output to the next full adder FA1, which has A1 and then complement of B1. So this is B1 complement and this is B1. Then the output here is S0, S1. Again, 2 more full adder I require for 4-bit addition. So this is FA2. Carry input is coming from the previous stage, A2, and then B2 bar. And this is A3, and this is B3 bar. So this is FA3. Okay, and here we have S2 and S3, and this is our final carry, which we call as C4. So C4 1, C2, C3. Okay, so I claim that this circuit can perform A minus B. So this is a 4-bit subtractor. The first circuit was a 4-bit adder, but they are now separate. Okay, so this is 4-bit adder. And to be more specific, it is a ripple carry adder, because you see the carry is rippling from one stage to another stage, and that is going to determine the delay of the circuit, which we have earlier looked at. So this is 4-bit subtractor. So subtractor means we are performing A minus B. Here we are doing A plus B. Now can we have adder subtractor circuit? That is what we wanted to do. So how can we combine these two operations in a single circuit? Okay, essentially we are using 4 full adders, and both circuits require 4 full adders. So instead of having a separate circuit for addition and subtraction, why not combine these two operations with the same set of 4 full adders? So that is our concern. So with that in mind, we can do slight modification. So now we are going to consider the final circuit, which is able to do the both operation. So again, it is going to have 4 full adders. Full adder 0, full adder 1, full adder 2, full adder 3. Okay, so if you want to add whether it is addition or subtraction, the A inputs are given directly in both cases, so there should be no change. Even after combining the both operation, we should have the A input exactly as before. Now one difference with respect to the carry input is that the initial full adder FA0 has a carry input 0 in the case of addition, and 1 in the case of subtraction. So we can consider it as some input which determines whether you want to do subtraction or addition. So this bit, which we call as C0, so this will be given as 0 if you want to do A plus B. Okay, that is addition is what you want to do, and if it is going to be subtraction, then we give it as 1 input if it is A minus B that you want to do. So it depends upon what operation that you want to do. So we will call this input as the mode input. Okay, so ultimately we have to tell the circuit subtract the 2 number or add the 2 number. So that is done by setting some bit equal to 0 or 1, and that is what we call as the mode input. Okay, so C0 is the mode input, and this connection between one stage to the other, this ripple carry propagation, that is same in both adder circuit and subtractor circuit. So we should connect C1, C2 and C3 exactly the same way, and finally you have your C4. And similarly, the output S0, S1, S2, S3, this also are taken out in the same manner. Only difference is that if it is addition, it's a positive number, and if it is a subtraction, it could be a negative or a positive number, but the result that you get here, they are in the 2's complement form. Okay, so we have to consider that the result here is in 2's complement form. So if you look at the MSB of this 4-bit result, and if you see that it is 1, then it is a negative result. If the MSB is the S3. If that is 0, then it is a positive result. Now there is also a case of overflow, which I will come into after the discussion of the entire combined circuit. Now A1, A2, A3, A0, these are given directly, but B1, B2, B3, B0, these are given after complementing in the case of subtractor. So we want to complement only when the mode input is high. Only when the mode input is high we want to complement it, otherwise we should not complement it. So which gate can complement in a conditional manner? Okay, so the answer is, so here we have a mode input and then here we have some BI. Okay, so what is going to be the output of this? So this output is going to be BI itself if M is equal to 0. So if mode input is 0, then the other input, if it is 0, it will come as 0. If it is 1, it will come as 1. Whereas if mode input is 1, then what is going to come out is BI bar. For example, if mode input is 1 and BI is 0, then output will be 1. So 0 will become 1. If mode input is 1 and BI is also 1, when both inputs are 1, the XOR gate will have 0. So therefore, when BI is 1, you get 0 at the output. When BI is 0, we get 1 at the output. So which is the complement of BI. So this is what we want. Okay. So here our mode input, which is our C0 here, same is given as one of the input of the XOR gate. So instead of NOT gate, what we do is we give 4 XOR gate. Okay, each XOR is a 2-bit gate. And it is a conditional NOT gate. Okay, that means it performs the complement operation only if the other input is 1. So the other input is common. It is the mode input. Okay, so wherever I put this dot means there is a connection. If there is no dot here, there is no connection. If it's just passing through it. So that is a convention that we will use. So here we give B0, B1, B2, B3. So the output of the NOR gate is like, if it is M is equal to say 0, then we have BI, or if M is equal to 1, we have BI bar. So this is the output. So similarly, whether it is B0 bar, B1 bar, B2 bar, B3 bar, that is going to come here. That is determined by the value of M0. So M0 is an external input apart from your A input and B input, which will decide whether you want to perform addition or subtraction. So this is the circuit which combines the operation of a 4-bit adder and a 4-bit subtractor. Okay, so if you want to add 2 negative numbers, then also you can use this circuit. Only thing is that then both A and B should be in 2's complement form, and the result is also to be considered in 2's complement form. Now there are cases of overflow which we have seen earlier in the theory part of the circuit. That time we did not consider the practical implementation, but we considered the cases in which overflow can occur. Overflow can occur basically when so let us have some discussion on overflow. So there are two cases where overflow can occur. If it is a 4-bit, we know that it can in 2's complement form represent 7 positive number, okay, 7 non-zero positive number, and then 1 0, and then 8 negative numbers. So overflow can happen if the result goes beyond +7, or if it goes below -8. Okay, so this will happen when two numbers that we are adding, one is both are negative. Okay, so case 1, if both A and B are negative numbers. Okay, if both the numbers are negative and the result is less than -8. So in that case overflow can happen. Similarly, second case in which overflow can happen is like if both A and B are positive numbers and the result is greater than +7, because the range of numbers that can be represented in 2's complement form using 4-bit alone is from -8 to +7. Okay, so -8, -7, -6, etc., then 0, 1 up to 7. So this is the range of numbers that can be represented in 2's complement form. Okay, 4-bit 2's complement representation. So these are the range. But if the result happens to be outside this range, then we say that there is an overflow. And if you go back to the theory classes, one thing I have shown you is that if you check the carry, so the carry at this stage and this stage, if you check these two carry, and if you use an XOR gate, okay, then you can detect overflow. Okay, so if you have forgotten this, you go back to the class and look at it. If these two carries are going to be different, then there is going to be overflow. So XOR gate can detect a difference if they are different, either 0 1 or 1 0, it will give you output. So here it is overflow. So overflow can be used to say whether any of these two cases has happened. Okay, so in one case what is going to happen is like you will have 0 coming at C3 and 1 coming at C4. So that will be one case of overflow. The other case of overflow is where C3 is 1 and C4 is 0. So these are the two ways in which overflow can happen. So to be more exact, if I think in this case, that is when you have a more negative number, what is going to happen is you will have C3 equal to C3 equal to C3 equal to 0. Okay, so the best way to check it is by taking an example. Okay, so if you have for example 6 and 5, plus 6 and plus 5, so let's look at plus 6 means 1 1 0. If you add it with 1 0 1, so the 6 plus 5 the result is going to be greater than 7, which is 11, that is greater than 7. So this is a case of overflow, so which is basically the second case. So if you do this, you'll be able to see that the carry that is going to come, this is 1, then 1 plus 1, 0. So this carry is going to be 1 here, and the final carry is going to be 0. So you can say in the second case you will have C4 equal to 0 and C3 equal to 1. Okay, so this is C3 equal to 1 and C4 equal to 0. And if you check the other case, you will see that this will be C3 equal to 0 and C4 equal to 1. So to see that case, you can take any negative numbers like minus 5, minus 6. Okay, so this will give rise to minus 11, which is lesser than minus 8. So that will correspond to the second case. Now what is minus 5? Minus 5 is you complement every bit of plus 5, so you will have 1 0 1 0 plus 1. So this is going to be 1 1 0 1. So 1 0 1 1, which is minus 5, and then to that you are adding minus 6. So minus 6 is going to be so minus 6 is going to be 1 0 0 1 plus 1. So that is 1 plus 1 0, carry 1, so which is 1 0 1. So 1 0 1 0. So this is minus 6. So when you add these two, 1 plus 0, that is 1, 1 plus 1 0, that is 1. And then here when you add, you don't have any carry here, that is 0. But 1 plus 1, that is 0, but there is a carry here. So you can see that so this is your C3, which is 0, and this one is your C4, which is 1. So that's what I said. C3 is 0 and C4 is 1. So that corresponds to the first case. So whenever you can consider any example, and you can check this out. If it is two positive number which is giving rise to a result less than 7 or 7 or less than 7, then like for example 2 plus 3, in such cases both will be 0 0. C3 is 0, C4 is 0. So which will give no overflow here. Similarly, if both are negative numbers and the result is also less than or equal to, or you can say greater than or equal to minus 8, then you will get 1 1. So this is essentially the theory behind the detection of overflow. So let's move on to the next circuit. Let's consider multiplier circuit. So 2-bit multiplier. So we have considered addition and subtraction. Now let's consider multiplication. So let's consider A is equal to A1 A0 and B is equal to B1 B0, and we want to multiply these two numbers. So what is the normal way in which we do this? We write A1 A0 and then we write B1 B0 under it, and then first thing that we do is we take the LSB of the so this one is called multiplier and this one is called multiplicand. So we take the LSB of multiplier, which is B0, and then multiply it with A0 first. So it is A0 B0. We take the product, which is basically an AND gate operation. Multiplication of single bit number, we know that that is similar to the AND gate operation. So only 1 into 1 is going to give us. So if I write the truth table, say, of a single bit multiplication, x, y, and x dot y, which is now taking a product. So 0 0, it is 0, 0 1, it is 0, and 1 0, it is 0, 1 1, it is going on. So this is exactly same as a x dot y or AND gate. Okay, so AND gate can be used to implement this product of single bit multiplication. And then A1, next one we will write here the next digit, which is A1 B0. Then we can take B1, the next significant bit of multiplier, and then write the product by shifting one step to the left. So this is the odd shift or shift odd multiplication algorithm. So you do A0 B1, and the next one is A1 B1. After adding this or after performing this product operation using single bit level, then you add them up and you will get A0 B0. Then you will have sum of these two. So let me just call it as P0, and then while adding you may get a carry at the second position. So P1, the next significant bit, which you have, say let's call it as C2, and that will have to be added with A1 P1 to get P2, and then if there is a carry, so that will be your P3. So this way, using 4-bit, you can take out the result. So how we can implement this? So each of this addition, for addition we can use full adders. If you want to add with carry, you can use full adder. If you want to simply add 2 bits, then you can use half adder also. So let us try to implement this. So you have an AND gate which is producing these partial products. So here you have B. Okay, so let me write like this. So this is my B0, and this is my A0. So this will be A0 B0. The next partial product that I require is same B0. Okay, and then A1. So that will give me the next partial product, that is A1 B0. Okay, so then I require let's take another AND gate. So this is B1, and then I need A0 again, so which is available here. So that is A0 B1. this is your B1 again, and then A1 I require. Okay, so that is your A1 here. So we have generated all the partial product term. Partial products are done using AND gate. Now comes the addition of these partial products. Okay, so P0, if you look at P0 is basically this itself. You don't need to do anything. So this itself is your P0. That is the first bit of the product term. The second bit of the product term, for that we need to add these two numbers, and to add these two numbers I can use a half adder. I don't need a full adder because there are only two bits that I need to add. One is this and the other is this. So that will generate two outputs. One is P1, the other is a carry output. That carry output I need to add it with another partial product, which is A1 B1. So I can use again a half adder. So that will give us P2. So two half adders are enough to perform this 2-bit multiplication, and this is my P3 finally. Okay, so this I hope is clear to you. If there is any doubt you can ask, and I will give you a homework. Implement a 3-bit. So homework, in a similar manner implement a 3-bit multiplier, and this multiplier, this architecture is called array multiplier. Okay, array multiplier, that's a name. There are various other multiplier also. So this is one of the simplest circuit. So this is so homework is implement a 3-bit array multiplier. Okay, and estimate the number of half adders and full adders required. Now in array multiplier, 3-bit case, as you can see when you write, there will be one more row that will be added, and each row will have 3 partial products. So therefore there will arise case where you need to add 3 bits together, and that can be implemented using a full adder. In this 2-bit addition case, we had only cases of adding 2 bits, and therefore half adder usage was enough. But for 3-bit array multiplier or 4-bit array multiplier, in a similar way you can continue with 4-bit also. There also you will require full adders in order to add 3-bit at a time. Okay, so that is your homework. Now let's go to the next circuit. Next circuit is Comparator. So let's start from the very simplest comparator, 1-bit comparator. Okay, what does it do? it will compare two single bits and tell whether they are equal uh, or which is greater than the other or which is less than the other. So let's compare two bits, let's say A0 and B0. These are two bits. So let me first show it like a black box. I'm not showing the detail inside. So I give an A0 input and a B0 input. Then I have three outputs. One is called G and the other is E and the last one is L. So this is single bit comparator. Now what is G, E and L? So G is equal to 1 if A is greater than B or A0 greater than B0. It is 0 otherwise. What about E? E is equal to 1 if A0 is equal to B and 0 otherwise. And what is L? Now you may know it is equal to 1 if A0 is less than B0 and 0 otherwise. So let us now write the truth table and then we can design it. So we are looking at 1 bit comparator truth table. So it has only two inputs which we took as A0 and B0. So there will be 4 combinations 0, 0, 0, 1, 1, 0, 1, 1. And there are 3 outputs. So there are 3 Boolean functions. They are called G, E and L. And G is 1 only in this case. All other case it is 0. E is 1 2 times. One is when both are 0 and the other is both are 1. Other cases it is 0. A is less than B. A is less than B only in one case, and that is this. That is A0 and B is 1. All other case. So this is the truth table. Now since it is only 2 input, so G as a function of A0 and B0, from the truth table you can simply write it as A0 B0 bar, A0 B0 bar. And what about E? E is a function which is also function of A0 and B0. It can be 1 in 2 different ways. One is both are 0, that is A0 bar, B0 bar. The other way it can be 0 is basically when both are 1. So that is A0, B0. And similarly the third output, which is a function of A0 and B0, is equal to, that is 1 only when A0 is 0 and B0 is 1. So these are the cases. So now we can implement this. And if you see, this is basically what we call as A XOR B, the whole bar, XNOR gate. 2 input XNOR gate. Alright, so let's implement this. We have A0, B0, this is A0, this is B0, and then so let us take the complement of A0 and B0. So G, we take A0, and then you take B0 bar. So B0 bar is here, and that is your G. Similarly, I can take L also. Only thing is I have to take A0 bar and B0. L. And then since this can also be written, E can also be written as A0 XOR B0 bar, why not let us take this A0 B0 bar plus A0 bar B0 the whole bar. So I just substituted the expression for the XOR gate, and then you take the NOT of that, that is XNOR gate. So which is basically, by comparing it with G and L, we can say this is G plus L the whole bar. So that is basically NOR gate. So that is your So you have three output. One is your G output, and E output, and N output. So 2 input and 3 output. So now if you want, you can put the box now to compare it with the earlier black box. So we have 3 output and 2 input here. So that is a single bit comparator. Okay. Next, design a 2-bit comparator using 1-bit comparator. So 1-bit comparator is given to us, and you are asked to design a 2-bit comparator. So 2-bit comparator means the number of input is now 2 bit each for each number. The first number is A, so we can call it as A0, A1 is the first number, and B0, B1 is the second number. So we want to compare these two. So what is the normal way in which we usually compare? We basically compare the most significant bit. The algorithm what we follow is we compare A1 with B1, and if A1 is greater than B1, we declare directly that A so this is A and this is B. So G is equal to 1 if G is equal to G is equal to 1. Under what condition? If A1 greater than B1. This is one way you can say G is greater. G is equal to 1. G equal to 1 means A greater than B. Or you could have another case where A1 is equal to B1 and A1 is equal to B1 and A0 is greater than B0. So this is the second way in which G can be 1. And all other cases we have G equal to 0. Now, if something has to be equal to the other, there is only one way it is possible, that each and every bit should be same. So this is equal to 1 if A1 equal to B1 and A0 equal to B0. It could be both 0, both 1, 0 otherwise. Okay, so then L equal to 1 if A1 is less than B1. You don't need to check anything else. You can declare that L is 1 or A is less than B. Or if they are equal, that is, if they are equal, A1 is equal to B1 and if A0 is less than B0. So this is an alternate way. L can be 1, 0 otherwise. Okay. So the question is like we are given 1-bit comparator and using 1-bit comparator we have to design 2-bit comparator. Now if 1-bit comparator is given, then we can find out whether A1 is greater than B1 or A1 is equal to B1 or A1 is less than B1. So all this information is available. So therefore we can write G, since 1-bit comparator is given, we can say that G is equal to 1 if G1 is equal to 1 or E1 equal to 1 and G0 equal to 1. So this way I can rewrite this 0 otherwise. And E equal to 1 if E1 equal to 1 and E0 equal to 0 otherwise. So this is what we are going to make use. This definition is what we are going to make use. And similarly L, that is overall less than condition, is equal to 1 if either L1 means the 1th position, that is A1 B1 comparison, if A1 is turn out to be less than 1, then this is 1, or E1 equal to 1 and L0 equal to 1, 0 otherwise. So we are given 1 bit comparator, and we are going to use this 1 bit comparator. Like a box. So here we are giving A1, B1. So it's a 1 bit comparator with G1, then E1, E1. And then another 1 bit comparator where you give A0 and B0. Okay. So this will give us G0, B0, L0. So we need some combinational circuit to take the output of these two comparators and combine it. So what is the way in which we can say overall A is greater than B? If you see G1 equal to 1, then you can directly say, or we can say if E1 is 1 and G0 is 1. These two are satisfied, then also you can say. So this is our G. Similarly, you can say if L1 is greater, you can say that is less than A is less than B, or if E1 is larger, E1 is 1, and then L0 if both of these are satisfied, then also you can say the number is less than. And what way we can say that the numbers are equal? Okay, so let me put it here. If both E1 and E2, if both are then also you can say. So you can see that it has 4 inputs and 3 outputs again, greater than, less than, or equal to. Okay, if it has to be greater than, there are 2 ways in which it can be. So that is given by this OR gate, either G1, that is MSB of the 2 numbers when you compare A1 is greater than B1. So then we don't need to check the LSB. But if they are equal, then we need to check the LSB. So if that is in E1 is 1, they are equal, A1 and B1 are equal, in that case we need to compare A0 and B0 and see if G0 is greater. So if E1 is greater, or E1 is 1 and G0 is 1, in that case also G can be greater, and the vice versa you can talk about L. And for equality, both bit has to be equal, that is E1 should be 1 and E0 should be 1. Okay. So similarly you have to do a homework. Design a 3-bit comparator given given 1 bit or given 3 1-bit comparator, given 3 like this, given 3 1-bit comparator. So you have to extend the logic to one more bit position. So there will be 3 1-bit comparator instead of 2 1-bit comparator like this. So there will be one more block here. Okay, so one block will compare A0 B0, another A1 B1, and another A2 B2, and each of them will have 3 outputs. So one of them you can call it as L0 E0 G0, then L1 E1 G1, then L2 E2 G2, and then you will have to find out the combinational circuit and combine them. So if you look at G, I will just give the combinational circuit connection here. So G is going to be either G2 or E2 G1 plus E2 E1 G0, and L is equal to L2 plus E2 L1 plus E2 E1 L0, and E is equal to E2 E1 E0. So that is what you need to do. Okay, so let's take a break.